Here's an electric circuit. We're asked to find the current leaving the battery. It consists of a 2 ohm resistor, and we've also got a 15 ohm resistor in parallel with a 30 ohm resistor. That's the parallel part of the circuit. How do you know that's the parallel part of the circuit? Well, we know when the current leaves the battery, it flows round this way, past the 2 ohm resistor, or through the 2 ohm resistor. When it gets to this point here, the current will split. And when current splits, that means there's a parallel part of the circuit. You can see that the current is going to be made up of the following. The current through the 15 ohm resistor will be double the current through the 30 ohm resistor, all because the 15 ohm resistor is half the resistance of the 30 ohm resistor. Now, to find the total resistance of the circuit, in order to find the current leaving the battery, we must work out the parallel parts of the circuit first. So we have a 15 ohm resistor in parallel with a 30 ohm resistor, and we have to work out the resistance of that part. So we'll call that 1 upon the parallel part of the circuit, and we'll draw two little lines to show this is the parallel part total of that circuit. And it's equal to 1 upon R1 plus 1 upon R2. That's our parallel resistor formula. 1 upon our parallel part is equal to 1 upon 15 plus 1 upon 30. We've only got two resistors in parallel. Now you can easily do that in your calculator, but you can easily see the fractions coming out quite good. 1/15 is the same as saying 2/30, and 1/30 we can put down just as 1/30. So 1 upon the total parallel resistance is going to be equal to simply 3/30. And that gives us the parallel part of that circuit is going to equal to 30 divided by 3. So it must give us a value of 10 ohms. So we can replace that 15 ohm resistor and 30 ohm resistor with a single 10 ohm resistor to make the circuit a little bit more simpler. And we'll do that now. There we go. We have the same circuit, but we've replaced the parallel part with our new combined resistance of 10 ohms. Now we can work out the total resistance of the circuit quite simply. The total resistance of the circuit is simply made up of R1 plus R2, because both resistors are now in series. The current is not splitting up as it goes around the circuit. We've made the circuit simpler. So the total resistance is going to be 10 ohms plus 2 ohms. Which is going to give us a total of 12 ohms. Now that we've got the total resistance, we can find out the current according to our Ohm's law. So I equals the voltage of the battery divided by the total resistance, which equals 12 volts divided by 12 ohms. So the current flowing around that circuit is going to be a current of 1 amp. So we know that the current moving around the circuit is 1 amp. So we go back to our other circuit, which is the same one. We can see the same thing. The current is going to be 1 amp. Now, say we're asked to find the potential difference across the 2 ohm resistor. Well, we look at a simple circuit. That's quite easy to do. We just put in our little characters. V standing for the potential difference across the resistor. I is the current through it, which we know is 1 amp. And the resistance of it is 2 ohms. So therefore we can quite rightly say that V equals I times R. So we're going to have 2 volts. So we're going to drop 2 volts across this resistor here. 2 volts. Now we know from our voltage divider circuit that if we drop 2 volts across the 2 ohm resistor, then across the 10 ohm resistor we must in fact drop 10 volts. And we're just doing that without even doing a calculation. To prove it, we could just simply put our V, I and R below the resistor to get organised. If we want to find V, we know the current through that resistor. The current is going to be 1 amp. The resistance is going to be 10 ohms. And the calculation proves us correct that the potential difference across that part of the circuit is going to be 10 volts. So, our circuit now looks like this. We know that there's going to be 1 amp leaving the battery, and across the 2 ohm resistor you're going to drop a potential difference of 2 volts. Across the parallel branches of the circuit you're going to drop a potential difference of 10 volts. And you can see the 10 volts across the parallel branch plus the 2 volts across the 2 ohm resistor adds up to give you the voltage of the battery. And we can prove that by going to our PHET site to see it for real. There's the same circuit, a 15 ohm resistor and 30 ohm resistor and our 2 ohm resistor. Okay, let's take a check of the potential difference across the 2 ohm resistor, and we have 2 volts. Let's take potential difference across the parallel branch of the circuit. And you can see it's going to be 10 volts as we worked out in our theory. And the key point to remember here is that if there's a potential difference across the branches of 10 volts, then that will be the potential difference across each of the resistor in that branch, provided there's only one resistor in the branch. So if we do that, we get a potential difference of 10 volts. If we come down to the 30 ohm resistor, we get a potential difference of 10 volts again. So now that we know the potential difference across each of the resistors, we can in fact work out the current going through each of those resistors. We'll go back and do that in our theory. Okay, here we have 15 ohms, 10 ohms across it, so we can work out the current through the 15 ohm resistor. We know the current through that resistor is going to be given by V divided by R, Ohm's law. So we have the potential difference across it, which is 10 volts, divided by the resistance of it, which is going to be 15 ohms. So we can reduce that to a fraction, and we can say that's the same as 2/3 of an amp. We'll just leave it as a fraction so we can see things a little bit clearer. So the current going through this resistor is 2/3 of an amp, which means the current going through that resistor must be 1/3 of an amp, because after all, going into the branch is a total current of 1 amp. So 2/3 of an amp plus 1/3 of an amp must give you the total current going into the branch. Let's check it out and see. The current going through the 30 ohm resistor, same potential difference divided by its resistance value, so it's going to be 10 volts, same potential difference divided by this time 30 ohms, which is going to give us 1/3 of an amp. And there's the theory all tying up. The 15 ohm resistor is going to take double the current of the current going through the 30 ohm resistor, just simply because the 30 ohm resistor has got the biggest resistance. So here's a complete circuit with all the values calculated in our circuit theory. You can see from the 12 volt battery that the current leaving the circuit is going to be 1 amp. That 1 amp is going to pass through a 2 ohm resistor, and therefore the potential difference across it will be 2 volts, and that's proven by using our voltmeter to show 2 volts. If we have dropped 2 volts over that part of the circuit, then there must be 10 volts dropped over the parallel branch part of the circuit, and you can see that there. The key point to remember is that if there's 10 volts potential difference across the branches of a parallel part of the circuit, then each branch will have the same potential difference. 10 volts across this branch, 10 volts across that branch. And that means that each resistor in that branch, provided there's only one resistor in it, will have the potential difference of 10 volts across it. So 10 volts across a 15 ohm resistor will give you a current of 0.67 amps. And across this one here we have the same potential difference. 10 volts across 30 ohms is going to give us 0.33 amps passing through that. So 1 amp passing into the parallel branch of the circuit splits according to the value of the resistance. Most of the current will go through the low resistance branch, and therefore depending on the values of resistance, as we can see here 15 ohms and 30 ohms, we can make a good estimate, or a very accurate estimate, that the current passing through the 15 ohm resistor will be double the current passing through the 30 ohm resistor. Circuit theory adds up and it works in practice.